Hello everyone, thank you for watching my presentation. My name is Ixchel Hernandez and today I'm going to be talking to you about modeling approaches to design diversified cropping systems at the local and landscape scale and the importance of considering within-field heterogeneities. The agricultural sector in Germany is quite relevant, as agriculture occupies about half of the land and it's highly productive. However, this has led to a series of environmental concerns, such as pollution of water bodies, increased greenhouse gas emissions, a decline of biodiversity, and increased yield risk. Some options to improve agricultural systems to promote the delivery of ecosystem services and biodiversity are crop diversification, which in a recent review it showed mostly positive effects on different measures of the cropping system, such as soil fertility, climate regulation, and biodiversity promotion. Additionally, new field arrangements using smaller fields can help to promote biodiversity. Accounting for within-field heterogeneities can also help to improve resource use, as crop allocation can be done according to the crop demands. Agroecosystem models can serve as an exploration tool to help on the design of newly diversified cropping systems. They simulate crop growth dynamics and are able to quantify certain ecosystem services. They can also be meaningful in evaluating the impacts from local to landscape scale. The first research question we would like to answer is, to what extent agroecosystem models have been used for crop diversification design at field and landscape scale by considering field heterogeneities? For this, we conducted a paper review. This table is a short summary of some of the findings. We found that at the local scale, agroecosystem models have been used for crop diversification, however, mostly for evaluation rather than design. At the spatial scale, two crop combinations are possible, with a minimum simulation unit of 1 square meter. They include already simplified crop interactions, however, it can be limited in the number of crop combinations. For the temporal scale, we found that more than 8 models are available and can simulate already between 13 to 70 crops, including the major crops. But some issues may arise with marginal crops and long-term simulations with regards to soil carbon dynamics. At the landscape scale, however, static decision-making frameworks are the most common. They include a diversity of crops. However, some limitations are that they are not dynamic and the diversification scale is limited to a field. We propose a framework for the design of diversified cropping systems that includes a static and dynamic part. In the first part, we conduct a field classification based on soil and chemical characteristics and select the range of crops to be used. These can be past crops or new crops. In the second step, we use the dynamic agroecosystem models to optimize the possible spatio-temporal combination of varying crops, field size, and field geometry. In the last part, we evaluate the trade-offs in terms of delivery of ecosystem services and possibly biodiversity promotion. An important factor on the design of newly diversified cropping systems is the inclusion of within-field heterogeneities. Therefore, a second question that we wanted to answer was the following. Is the model capable of simulating crop responses to within-field heterogeneities? For this, we use the patch crop experiment, which is our main source of data, and we use the window 1, which corresponds to the business as usual production practices. Here you can see the list of input data that we use for the model calibration, including climate, crop variables, management, and soil conditions. We conducted a simulation for 3 crops, maize, soybean, and winter wheat. We used 2 contrasting soil profile descriptions from the patch crop experimental site. You can see the descriptions here. Basically, the first soil profile shows a loamy layer at 53 centimeters, which has a positive incidence in water retention characteristics, while the second profile has a higher percentage of sand over the whole soil profile. And the simulation was conducted for 10 years. For the top biomass and yield in the top right, you can see the 10-year summary. The yield is in clear color and the top biomass is in dark blue. You can see here the absolute numbers and the percentage differences. You can see here that in average, the high yield potential soil resulted in higher top biomass and yield by between 20 to 40%. Similarly, in the bottom right, leaf area index increased also by about 35% in the high yield potential soil. If we look at the yield temporal dynamics of the 10 years, here to the left, the dark line is the high yield potential soil, the green is the low yield potential soil, the blue asterisks are the years with the higher seasonal rainfall, and the red ones are the ones with the lowest rainfall. And we have again maize, soybean, and wheat. We can see that for almost all the years, the high yield potential soil resulted in higher yields. Maize appears to be less sensitive to these soil differences, but for soybean, we can see that for the drier years, the crop performs better in the high yield potential zone. Similarly for wheat. Some of the key findings for this last part were that the crop responds in different magnitude to the soil types. The appearance of the loamy layer plays an important role also in the soil water retention characteristics and therefore in the water stress for the crop. Proximal sensing can further help to provide information on soil characteristics, such as the appearance of the loamy layer, which seems important in terms of water relations. And there is a potential to use agroecosystem models to simulate within field heterogeneities. For our final expected outcome, we expect to provide and gain mechanistic insight into scale-dependent effects of crop diversification on agroecosystem performance, and also to develop and apply agroecosystem models to study and optimize diversified cropping systems at the local and landscape scale based on the trade-offs of productivity, ecosystem services, biodiversity, and economics. Thank you all for your attention, and see you at the live questions and answer session. Bye.